This is a neuron. It is one of the cells that occupies the space that is your brain. We can break it down to dendrites, the soma, the axon, and the axon terminal. Let's start with the dendrites. Here we have two neighboring neurons. They are able to send excitatory signals down onto the dendrites of our neuron, which receives them through receptors that basically create a electrical current downstream through the dendrites and onto the soma, all the way to where the axon begins. This area is called the axon hillock. So let's go ahead and call that the axon hillock. In this region, we have a resting membrane potential of, let's say, negative 70 millivolts, but its threshold is, let's say, negative 50 millivolts. So the electric current is able to basically connect with this axon hillock, and if the electrical charges are able to bring the voltage up to negative 50 millivolts from negative 70 millivolts, then we can have an action potential. So let's assume that the electric current has indeed made the resting membrane potential higher and reached the threshold of negative 50 millivolts. From here, we can see that a lot of sodium will start entering the cell. Let's go ahead and go with this. So sodium channels just start opening up dramatically because there's a lot of them present within the axon hillock. So a lot of these sodium ions, they start going inside. And as a result, it brings the voltage up much higher from the negative 50 millivolts. So from here, it's able to go, let's say, at its peak, it could be a voltage of 30 millivolts plus 30 millivolts. Let's say this is peak. So now that sodium has rushed in, we can see that the electrical current continues down the axon. And so one thing we need to know is that the axon is covered by these little bubbles, these little fatty substances. And these are actually called Schwann cells. These Schwann cells are basically able to insulate the axon so that the electrical activity does not come out, because if it does, then we lose all the electrical activity that we have going on. And as such, it's able to preserve this current from leaving, and also makes the current travel faster. So let's go ahead and call these the Schwann cells. So at this point, all we have is basically sodium has come in and has created a current that has gone down the axon, and it goes through these let's say this first Schwann cell. Let's focus there. In this first Schwann cell, there is a gap here. These gaps are called nodes of Ranvier. Let's go ahead and write that down. Nodes of Ranvier, where there's a lot of sodium channels. So as the electrical activity is going through the Schwann cell, it is able to propagate quickly. It's called saltatory conduction. And it's able to reach this area, this node of Ranvier, where there's no insulation. However, this is necessary, as in this area, there's a lot of sodium channels. And since this signal is already going through this Schwann cell, it is still dying out. So we want to preserve it as much as we can. So we add some sodium channels here, which are able to bring in more sodium and basically start the process all over again of sodium entering the cell and creating a peak of 30 millivolts in this area. And as such, this signal continues propagating down the axon, where at each node of RAMVA, it is again supported by sodium channels coming in, sodium channels opening and sodium coming inside, which again creates more current, and then again more current, and again more current. So then the signal was able to continue being constant as a result of the resuppliance of sodium ions at each node of RAMVA. So now that our signal has reached the axon terminal, let's focus on this little area now. The electricity is able to run through into the axon terminal. And at this point, there are little receptors around here. And these receptors are able to open for calcium to rush in. They go inside of the axon terminal, and as such, let's say over here we have some proteins. They are basically able to act on these proteins, which ultimately leads to, let's say these are some synaptic vesicles which carry important information. They have chemical messengers inside. And the proteins are able to then start acting on these vesicles and basically grabs them and brings them outwards through a process called endocytosis. And as such, it's able to release all these chemical messengers from inside. And these chemical messengers, they basically go through this called the synaptic cleft. It's called this little area where there's nothing. It's just open space. The synaptic cleft, where there's nothing here except another neuron at the other side. And this neuron is able to have receptors. These receptors are able to accept these brown ions. Or sorry, not ions. Brown chemical messengers, which are then able to activate the receptor and create another electrical current downstream of that neuron. So let's start at the beginning. We have the dendrites that, upon receiving an input, are able to create an electrical activity that activates the axon hillock. If the electrical charge is high, then we are able to reach the threshold after the resting membrane potential. And if that's the case, then a lot of sodium starts coming in, which ultimately peaks around 30 millivolts. The electrical activity goes through the axon. There are these Schwann cells that insulate the axon and are able to preserve the signal and are able to move the signal quickly as well. However, over time, the electrical activity starts leaving the cell. So to preserve it, there are sodium ions that are able to go through these sodium channels in these locations called nodes of RAMVA, which basically just are there to resupply the sodium need to maintain the electrical activity. And as such, the electrical activity continues forward through the axon onto the axon terminal. And at the axon terminal, we see that the electrical activity is able to activate these channels that bring in calcium. And the calcium is able to act on proteins that move the synaptic vesicles that contain chemicals called neurotransmitters outside of the cell. And once these neurotransmitters are released, they're able to head towards the other neurons that are near it through this so-called synaptic cleft, whereupon it can reach these receptors and activate certain channels that ultimately create a electrical activity to head down this other neuron's dendrite. And so there you have it. This is the neuron. These little processes are going on all the time inside your brain.